Hi everyone. We finished chapter 4 and we have solved the consumer's utility maximization problem. We are now ready to derive the demand curve for the consumers. So in this video, we are going to first derive the demand curve. We will see what happens to the demand curve as the income of the consumer changes. And we will also derive the relationship between income and the good that the consumer will consume. And this relationship is the angel curve that we can draw. Lastly, we will define what is meant by a normal good and inferior good, and how we relate those two concepts to the angel curve. You probably have learned this in Econ 3 already, so the third part is going to be quite straightforward. And before we actually start discussing anything, I'm going to ask you a question that you might have already seen in Econ 3, and you are able to answer this after Econ 3. You don't need to have learned today's lecture to answer this question. And this is the first extra credit question for this week. So let me read the question. The demand curve is usually assumed to be upward sloping or downward sloping because if the price of the good increases, the consumer will choose to consume more or less of the good. So you can submit your answer on iLearn to earn extra credit. All right. So in last week's in the last video, we have solved this utility maximization problem. So we have a utility function that is u equals to the square root of x times y. We have income, the price of good x, and then the price of good y. With those numbers, we solved last time that the optimal bundle, the optimal consumption bundle for the consumer is 20 and 10. So what happens if the price of good X increases to 25 and hold all other conditions the same? So as a review and also as a motivation to today's class, I'm going to solve this question again in the next slide. All right. So we know that this utility function is a Cobb-Douglas utility function. So we can use the tangency condition that we derived last time. And let me emphasize again, you should only apply the tangency condition when you see a Cobb-Douglas utility function. Otherwise, there is no guarantee that the tangency condition will work. So the tangency condition is going to equate the marginal rate of substitution, the slope of the indifference curve to the slope of the budget constraint. And effectively, it is equating the ratio of MUX to MUY to the price of good X over the price of good Y. Now with this utility function, we can calculate the derivatives and find the marginal utilities. And I'm going to skip the steps where we calculate the marginal utilities. So the ratio of MUX to MUY is going to be Y divided by X. And we are equating this to the ratio of the price, that is 25 divided by 40. So this tells us that Y equals to, well, 5 divided by 8. So 5x divided by 8. And for this relationship, we have a name for it. It is the optimal ratio. And we are going to combine the optimal ratio with another condition that the optimal bundle, the optimal consumption bundle, must lie on the budget constraint. Because, well, this utility function satisfies the assumption that more is better, right? So the consumer will not want to have any income that is unspent when consuming the optimal bundle. So the optimal bundle must be a point that lies on the budget constraint. We call this condition 1. The condition 2 is the fetched that the optimal bundle on the budget line, I should have said. So this will mean that 25x plus 40y equals to 800. And let me call this the second condition. To solve for the result, we can substitute 1 into 2. So substitute the first equation into 2. What do we get is that 25x plus 40 times y, and now y is 5x divided by 8. So it is 5x divided by 8. This has to be equal to 800. We can simplify the equations and solve for x. And we will find that x equals to 16. If I call this equation 3, we can substitute equation 3 back into equation 1. And this is going to give us y equals to 5x divided by 8, which is 5 times 16 divided by 8, and it is going to be 10. So we have solved for the optimal bundle here. X equals to 16, y equals to 10. So the optimal bundle is x, y equals to 16 and 10. All right. The steps are identical, only the numbers are different to what we did last time. And I go through all those steps just to provide a review of the steps. You would want to practice solving this question of similar type, and also questions when the utility function is not crop-dot-less, but perfect substitute and perfect complement several times to make yourself more familiar with what is going on. So we can solve for the optimal bundle here, that is 16 and 10. Let me clear those actually. All right, so we have been solving the optimal bundle for different values of px, the price of good x. So what we did is that, well, holding the income and the price of good y the same, when the price of x is 20, the optimal bundle is 20 and 10. And when the price of good x increases to 25, the new optimal bundle is 16 and 10. We did 2, but we can potentially do the same exercise for all different possible values of px, right? And what we can derive is a relationship between the price of the good x and the amount of good x, as well as the amount of good y, that the consumer will choose to consume. And here by choose, the consumer is solving her utility maximization problem. She is making an optimal choice. And this relationship, does this look familiar to you? It is exactly the demand curve for the consumer. It is the quantity of good x that the consumer will consume, the consumer will demand, based on the price of good x, holding some outside conditions constant, which is, well, the consumer's utility function. We are not changing that. The price of the other good of concern, which is the price of good y, we are holding that constant, as well as the consumer's income, right? We are holding those outside factors constant, and we are deriving a relationship between the price of the good x and the quantity of the good x that the consumer will choose to consume as a result of her utility optimization problem. So this is how we can derive the demand curve from the consumer's problem. And In Econ 3, you learned various properties and models about supply and demand curve, but we didn't derive that. So here we are eventually ready to show you how we derive the demand curve. So previously, we were still using numbers, so in this slide, we can, instead of using any numbers, we can replace those numbers with letters and derive everything algebraically. And because all the steps are very similar, I'm not writing it down again, but I've typed it on the screen. So we start from using the tangency condition to derive the optimal ratio between y and x. And we can see that the optimal ratio of y and x depends on the ratio of the price of good x to the price of good y. So the second condition is that the optimal point has to be on the budget line, as I've been doing in the previous slide. So combining the condition 1 and condition 2, or we can substitute the optimal ratio into the budget line, we can find the optimal, the amount of the good x that the consumer will consume in the optimal bundle. So in this general case, we see that the amount of good x the consumer will consume is I divided by 2 times px. So it depends on the value of her income as well as the price of good x, which are very reasonable. And note that it is a special case, it is a special result of the utility function, the Cobb-Dodders utility function, that the consumer's demand for good x do not depend on the price of good y. All right, this is a special feature of Cobb-Dodders utility function. In general, this need not to be true. So recall in Econ 3, you probably have learned that if the price of the substitute of the good increases, what will happen to people's demand for the good? So if the price, so let's say if the price for Pepsi increases, likely people will demand for more Coke, right? So the demand for X, the demand for Coke depends on the price of the other good, the price of Pepsi. And in that case, people's preference over Pepsi and Coke are probably not going to be represented by the Cobb-Dodders utility function, because the result, well, is a violation of what actually happened in reality, right? So this, the fact that the equation 3 is really a special feature of Cobb-Dodders utility function, and you should not take this for, and you should not think that this holds in the general case. And lastly, we substitute the optimal amount of good x that we derived into, well, either 1 or 2, but 1 is easier. So we substitute it into equation 1. So y equals to px divided by py times x, and x is I divided by 2 times px. So the optimal amount of y the consumer will consume is I divided by 2 times py. And similarly, also because of the symmetry, the demand for good y does not depend on the price of good x as well in this example, but again, this is not true in general. So the optimal bundle for the consumer is xy equals to I divided by 2 times px and I divided by 2 times py. And I put a note that I can emphasize more that this expression really depends on the utility function, and different utility function will represent people's preference over different kinds of goods. So this expression is really a special case of this utility function and is definitely not the general case. I'm using it as an example to show some of the things in this lecture. The demand curve can also be viewed as a willingness to pay measure. So the point on the demand curve tells us how much the consumer is willing to pay at consuming, well, different points of the consumption bundles. So from, let's go back from the letters to numbers a little bit. So from So let's say the income is 800. The price of good X is still PX, and the price of good Y is PY, and let's say that is 40. In the previous slide, we derived that the optimal bundle is I divided by 2PX, I divided by 2PY. And substitute in the numbers, the optimal bundle is 400 divided by X and 10. Let's ask a slightly different question to the consumer. So let's ask how much is the consumer willing to pay for an additional unit of good X? Well, and we note that her answer is probably going to depend on how much she is actually consuming right now, right? So if she is already consuming a lot of good X, while very few of good Y, she's probably not willing to pay as much for an additional unit of good X as compared to when she is consuming very few units of good X, but many units of good Y. And of course, this is a very rough statement. It also will also depend on the price of the good Y as well. So let's fix the point that she is consuming right now. So let's say she is consuming 20 units of good X and 10 units of good Y. And note that this is the optimal point we derived previously, and I'm using this special point for a purpose. So let's ask how much is the consumer willing to pay for an additional unit of good X at this point, fixing that her income is 800 and the price of good Y is $40. So how can we answer this question? Let's recall the two expressions. That is the MUX divided by PX and MUY divided by PY. So previously we have been using this to determine if a point is an optimal point. So those two expressions tells us the additional utility the consumer would obtain if she spent an additional dollar on either good X or good Y. And only when those two are equal, the consumer cannot make her better off, right? Otherwise, she can increase the consumption of the good so if MUX divided by PX is higher than MUY divided by PY, she can increase her consumption of good X and decrease her consumption of good Y slightly, only slightly. And only slightly is enough, and doing so will allow her to increase her total utility. So those two must be equal at the point where the consumer is making an optimal choice. So this expression becomes useful when we are trying to answer this willingness to pay question. So previously we were just calculating, or we were looking for the point that the equation hold, and we are taking PX and PY as given. Now we are looking for a value of the price of the good X. So the amount that the consumer is willing to pay for an additional unit of good X is basically the price of good X. So we are looking for the value of PX that will make this expression, that will make those two expressions equal at the point of 20 and 10. And we can imagine that if the value we find is higher than the actual price of the good X, then the consumer will be choosing to increase her consumption of good X by slightly, right? And vice versa, if the value we find is actually smaller than the actual price of good X, then the consumer will probably be willing to give up some consumption of good X in exchange for the money that he spent on good X, because she is not as willing to spend as much on the good X as the price of the good X actually is. And when this point is an optimal point, we can imagine that the value we find for this question must be the actual price of good X. So let's actually solve this question here. And I said on the slides that the solution must be Px equals to 20. I don't have to solve it because we know this is an optimal point. and that on the demand curve, Px equals to 20 when x equals to 20. But let's actually solve this problem over here. So given the utility function, mu x equals to the square equals to half times the square root of y divided by x. This divided by Px equals to mu y is half times the square root of x divided by y divided by py, and py is 40. And I'm also going to substitute x and y being 20 and 10 into this expression. So this is saying that half times the square root of 10 divided by 20 divided by Px equals to half times the square root of 20 divided by 10 divided by Py, which is 40. So everything else is number. The only thing that is unknown is Px. So I'm going to cancel the half on both sides. I'm going to multiply 40 times Px to both sides. So it becomes the square root of 10 divided by 20, which is 1/2. Equal, this times 40 equals to square root of 20 divided by 10, which is 2, times Px. And we can divide both sides by square root of 2. So this is going to be square root 1, 2 times 2 after we divide both sides by square root of 2, and multiplied by 40 equals to Px. And this is going to say exactly that Px equals to 20. All right, so all of these that I did over here is, well, solving this equation. And as I was saying, I know that because 2010 is an optimal consumption bundle, then so the solution must be Px equals to 20, because on the demand curve, Px equals to 20 when x equals to 20. So what is the demand curve? Let me draw it over here. The demand curve is basically x equals to 400 divided by Px. So on this graph where we have x and Px, the shape of the curve is not going to be a straight line. It is a little curved. Oops. It looks something like this. And when the point 2020 is on the curve. So when x is 20, we know that the person's willingness to pay for an additional unit of good must be $20. So this is how we can interpret this demand curve as a willingness to pay measure, all right? So we have done all the hard work before. We are now ready to talk about change in income, which is going to be much more straightforward. So again, I'm using this example here. We have a utility function that is Cobb-Douglas, and we have derived that the optimal bundle takes this form. So in Econ 3, we learned that when the income of when the person's income increases, the person's demand curve will shift to the right. We can draw it on this graph over here. So for different levels of income, basically we are looking at different values of I, and on the horizontal axis is our quantity. On the vertical axis is our price of good X, PX. So this describes our demand curve, right? The relationship between PX and X. So for different values of X, the demand curve, which, well, in this case is not a straight line, are going to be something like this. So this is when income equals to, well, some level of income, I1, and when income changes to a different level, I2, we see a shift of our demand curve. And we can not only draw the shift of the demand curve, we can also describe directly the relationship between our income and our demand for good X. And we call this curve the angel curve. So the angel curve describes, so I probably should have typed over here, this is the relationship angel curve is the relationship between people's demand or people's optimal choice of consumption of good X and her level of income. So now, on the axis, we have different axes now. So previously, we always have X on the horizontal axis. Previously, on the vertical axis, we have PX, remember? In the last slide, we have PX. But now it is going to be I. So this is the angel curve describing the relationship between income and X. And if we have those two on the axis, we can see that it is actually a straight line in our case. And again, this depends on the expression depends on the utility function. All right. And ultimately, the utility function represents people's preference. So when people's preference become different, well, the demand curve might look different. The angel curve might look different. And it represents people's different preferences over different types of goods. And in this case, when we have a Cobb-Douglas utility function, we have an algebraical representation. We solved the equation algebraically, and the angel curve happens to be a straight line. So in this case, the angel curve is going to be a straight line. And we can rewrite this equation a little bit. So it can be rewritten as I equals to 2px times x. Times x. So the slope of this is actually 2px. Slope equals to 2 times px. But again, this depends on the utility function. This is a special case. But in general, we can solve our utility maximization problem many times for different value of income, and we can plot our solution to those problems on a graph like this. That is the angel curve. And lastly, we are going to define, we probably have done so already in Econ 3, the normal good and the inferior good. So normal good are good that the consumer purchases more of it when her income increases. And reflecting on the angel curve, it is an angel curve that has a positive slope. And for most of the goods, we would consider those as normal good. And inferior good is a good that consumers purchase less as income rises. And reflected on the angel curve, it is an angel curve that has a negative slope. So an example of inferior good are usually some good of low quality. So it can be either junk food or maybe clothes of low quality. And we can imagine that when people's income is low, people have to rely on those goods to survive. But as long as people's income become higher and are available to afford goods of higher quality, which are potentially more expensive as well, people will substitute those good of low quality with good of higher quality, so that when people's income rises, the amount of good of low quality that people purchase will become less, making those good inferior good. To summarize what we did in this video, we derived the demand curve for consumer based on the utility maximization problem. And we described that the demand curve can also be viewed as a willingness to pay measure. It tells us that at different level of consumption of each good, how much is the consumer willing to pay for an additional unit of the good. We reinforced what we learned in Econ 3, and we explained that we actually derived that the change in income can shift our demand curve. And if you remember, the change in the price of the good is going to cause movement along our demand curve, right? So the change in income can shift our demand curve. And also we can directly derive the relationship between income and the good that people consumes. And we call this the angel curve. And lastly, the normal good and inferior good refers to two types of good that has either a positive or negative slope of the angel curve. So this is all for this chapter.